Hey kiddos, I'm going to try to make this relatively short. I know that there was actually a lot more to the reactions of alkenes, but I know that some of you missed part 2 in class, so I'm going to go ahead and make a quick video just to sort of fill you in on the gaps that you might have, and then hopefully at some point I'll go back and actually fill in all the other videos. That is the plan. So we left off talking about Markovnikov's rule as in electrophilic substitutions as one, or electrophilic additions as our main type of alkene reactions. But there are some other types as well that are really important to us. And one of those is something called hydroboration of alkenes. Now, the way this works, and actually I shouldn't add that in, sorry. The way that this works is that we're going to add a borane, which is BH3, to an alkene. Okay, so we got our generic alkene here. In this case, I happen to put the double bond on the end. Doesn't necessarily have to be, but that's just going to show us what's going on pretty easy here. And of course, the R. So the way this works is we're going to bring in our borane molecule and we're going to try to attach it to the alkene. And the way this is actually going to work is that this is what's called a concerted mechanism. In other words, the mechanism that we talked about in Markovnikov's rule, it happened in these specific steps, okay? So the hydrogen attacked, it formed a carbocation, the nucleophile attacked the carbocation, and then we got our final reaction product. And so it was sort of a step-by-step process. This happens, then this happens, then this happens. In a hydroboration, basically everything happens at once. The hydrogen is going to bond, the boron is going to bond, and we're going to get our end result here. Now, what you may have noticed here is that I didn't put anything off to the ends here. According to what we have so far, of course, then that's just going to be a couple of H's, okay? But what we'll see is that we don't just have to do this reaction once, that we can add multiple moles of alkenes to our borane, and we're going to get a different sort of reaction. And so I want to illustrate that because that actually lends to what is really useful about these reactions. What's useful isn't just the product right here, but what we can then turn that product into. So if we take 3 moles of a simple alkene like propene, okay, we add it to our borane, then what we're going to get out of that is essentially boron at the center with 3 alkane groups hanging off of it, or as we know now at this point in the year, 3 propyl groups hanging off of that. Now, that in and of itself isn't what's super important. What we're going to do is we're going to treat this product then and then create something that is important to us. Okay, so this is the same molecule. Okay, so just in case you're a little bit confused, this, okay, is that guy, all right? And so we're going to treat that with a couple of important things here. We're going to treat it with a base, and it doesn't have to be sodium hydroxide, but that's a pretty common base for us. And then in addition to that, what really makes this happen is we're going to treat it with hydrogen peroxide, okay? And hydrogen peroxide, we'll see in a little bit, can have, or peroxides in general, can help a lot of reactions along. And so we're going to do that peroxide and a base, and what we're going to get is an alcohol, okay, in this case propanol. Now you might be looking at that going, aren't there other ways to produce alcohols? And we'll certainly learn a lot more when we get to alcohols later in the year, and the answer to that is yes. In fact, if you think back when we talked about hydration, where we're adding water to alkenes, we were also making alcohols there. And so you're like, well, I don't really see what the point then of this, why would we do it in this multi-step process? Why wouldn't we just do a hydration reaction? Well, here's why. So if I did the traditional hydration reaction, okay, so added water in the presence of acid, okay, to our alkene, then what I would get is our typical Markovnikov product. In other words, the hydrogen's going to come out here on the end. We're going to form the carbocation in the more stable state, which is going to be the carbon with the most connections. Hydroxide then is going to attack that part. And what the result is going to be is that we're going to get our OH, our alcohol group, our hydroxyl group, attaching here, not at the end carbon, but at one of the carbons in the middle. So why then will we do our hydroboration reaction? Well, if we do the hydroboration 2-step thing, then what we get is what's called an anti-Markovnikov product. And what does that mean? Well, in this particular case, what it means is that I get my hydroxyl group on the end, okay? It's not in the middle carbon, which is the more stable way for it to happen if we're hydrating it, but it happens at the end. And so we get, for instance, if this was a CH3 here, okay, if this was our propene from our previous example, we'll make that one that too. If this was our propene, this is isopropyl alcohol, and this is what we would call straight chain propanol or 1-propanol. And those are slightly different compounds. They're going to react a little bit differently in their cases where we want this straight chain alcohol as opposed to this isopropyl alcohol. And we can't get there just by hydration, but we can by hydroboration. This is one of the things that makes upper level chemistry really cool, is not just to talk about the stuff that we do and just some of the calculations, but how can I get to the end product that I want by maybe doing a series of different types of reactions? I know I can't get there in one step, but if I do a bunch of steps differently, then I can get there. Okay, so that's one of the important things to remember about this hydroboration, is this is how we're going to get an anti-Markovnikov product. This is how we're going to get our straight chain alcohols, as opposed to our alcohols in the middle of the compound that we would get just from hydration. Okay, so a couple other quick reaction types. This one is super important. This is hydrogenation. We're going to talk a lot more about hydrogenation next semester when we talk about biochem and lipids, because obviously this has a lot to do with when you hear about trans fats and partially hydrogenated vegetable oils and stuff. This is the hydrogenation that they're talking about there. And so what happens is we've got some sort of alkene. We're going to add hydrogen to it. This doesn't happen on its own. We need a catalyst. Usually that catalyst is some sort of a metal compound, quite often something like platinum. And what's going to happen is we're going to basically break the bond, okay? So our bond that would normally be here, we're going to break that, okay? And where that was, we're then going to attach two hydrogens. Now, what you should notice immediately, this is different than us adding hydrogen to our alkanes, because in alkanes it was a substitution. You're pulling a hydrogen off. I'm sorry, you're pulling in substitution, you're pulling a hydrogen off and you're adding something like a halogen or something like that in. In hydrogenation, you're just breaking the bond, and the breaking of that bond frees up some electrons so that then you can add something as simple as hydrogen to it. And obviously that would lead you to believe, well, hey, I can add some other stuff to it as well in the halogenations, and that is true as well. What is important to us in this process is that usually this is going to happen on the same side of the bond where that matters. Now, here it doesn't matter. If I added my hydrogen up here, since this is a single bond, we could just rotate that, right? And so there's no real cis or trans around a single bond. Where that would matter is if we had something like, say, a cyclic compound. Okay, so let's say that I had cyclopentane in an amazing drawing. Apparently I was drawing Superman shield. But then it matters, right, if I add both of the hydrogens on one side, or if I add one going this way and then one going that way, and that's a trans. So that would make a difference. But typically in hydrogenation, we're pretty much always going to get cis compounds when this is actually performed. Remember, too, that you have to have a catalyst. So if you're asked to, say, draw one of these reactions, you got to throw a catalyst of some kind in there. And you can, I mean, the easiest thing to do, honestly, unless you're told otherwise, is just, just throw platinum in there. Okay, that one's pretty easy to remember. And that'll be your catalyst. So I want to just introduce conjugated systems. We're going to talk more about this in the next video. And I think as far as what we did in class, most of you all were here for Diels-Alder reactions. But this is how we get to Diels-Alder reactions. If you remember back when we talked about alkenes, one of the things that we said is that we could put the double bonds in certain ways, and then it made different kinds of compounds. And if you recall, if we have alternating double bonds, we call those conjugated systems. Okay? So in this case, I have a 1,3 double bond. This is butane, right? And so if I was going to name this, this would be 1,3-butadiene. Okay? Butane, because there are 4 carbons. I've got 2 enes, right? So 2 double bonds there, and so that's going to be the diene part. Carbon 1, carbon 3 is where the bonds start, and so that's 1,3-butadiene. And so what would normally happen to that, according to our Markovnikov rules, is that if I broke one of those double bonds, okay, just one of them, by, say, adding an acid to it, that the hydrogen's going to add to the outside one, right? We're going to get a carbocation here. The bromine is going to add there. And that is what we would call traditional 1,2 addition. However, what we find when we actually do these reactions is that that's not all we get. We get this really weird product that isn't what we think we should get at all. This is what's called 1,4 addition. What we get is the hydrogen adding on one end, the bromine adding on the other end, and this double bond that was over here at the 3 shifts over to the 2. And that is incredibly strange, right? Because we're like, well, I mean, we've talked about adding stuff, but we haven't talked about like a bond moving where it was. We've talked about breaking them, but not shifting where it is. So I want to real briefly talk about this mechanism, and then of course we'll talk about it more when we get to Diels-Alder stuff as well. So the mechanism for this 1,4 addition is essentially this. So this is the normal way that it would happen, right? We add a hydrogen on, okay? So this H right here, sorry guys, I'm going to get a pen real quick. This H right here becomes our third H right here, okay? And that's going to give us a carbocation on that second carbon, okay? So a positive charge on that second carbon. And normally we would say, hey, that is where that bromine would attack in our previous example. Okay, but let me show you what can happen though, and this all has to do with resonance. So normally this is what we would get, but remember when we've got a double bond that could be in a couple of different places? Okay, we get a resonance structure, right? And so what can happen is that the two electrons that are here in this end bond can actually shift to the middle, and when that happens, okay, that actually gives us the carbocation on the end, the opposite end of the molecule, okay? So this is where we added the hydrogen over here, but we get a carbocation on the other end. And so what we see here is a resonance structure. And remember, the idea behind resonance is that both of these things are possible, right? It's not like just one of them is there. They're both basically existing at all times. And so since that happens, what you can see here is that if we go in to add our bromine, there are two possible ways that I could put it in. I can put that bromine here in a traditional 1,2, or I could put that bromine over here and do a 1,4 addition, okay? And so remember that when we get that, when we have that 1,4 addition as opposed to 1,2, that it's solely the result of the resonance structures, that the electrons in the double bond can shift and basically shift where the double bond is in the molecule, okay? And so that's how that's going to happen. Later on, we'll talk a little bit more in our next video about Diels-Alder reactions and how this actually helps us to build some really cool cyclic compounds. All right, thanks, guys.